Hi guys, so now that we're done laying the foundation for digital electronics and Karnaugh Maps and Boolean algebra, now we're going to jump right in and try to solve a handful of questions on Karnaugh Maps. So that's what we're going to be doing today. This is the first part. We're going to solve much more, but this video is we're going to take to one for 3 variables and one for 4 variable Karnaugh Map. So let's get right into it. Using a Karnaugh Map, simplify the following Boolean expression. X is equal to not AB, or not A not B C, or AB not C, or A not B not C. The first thing we have to figure out, that we have to learn how to figure out, is that this is a non-standard SOP. Okay, so non-standard SOP. How do we know that? This first product term, not AB, does not include all the terms of the domain. The domain of this function, domain of X, includes A and its complements, B and her complements, and C and her complements. So this first term includes not A, B, and has nothing in terms of C. So what we're going to have to do now is to convert non-SOP to standard SOP. So I covered this in the last video. I'll link this in the right here, the top right corner. So now we need to learn we have to try to convert this non-standard SOP to a standard SOP. And that's actually pretty simple. So X is now going to be not AB into C or not C, or not A, not B, C, or AB not C, or A not B not C. So we have to expand the first bracket term. So that's going to give us not A, B, C, or not A, B, not C, or not A, not B, C, or A, B, not C, or A, not B, not C. So let's write this out so we have a clear view of the final expression we're working with. So this is going to be not A, B, C, or not A, B, not C, or not A, not B, C, or A, B, not C, or A, not B, not C. So what we've been able to do here is to convert the non-standard SOP expression here into a standard SOP, like we did in the video before this. Now the next thing is to write this into our Karnaugh map. So we start from here. This is not okay. So the domain is, let's cover how to build a Karnaugh map. You first of all look at your domain. How many variables are in your domain? So we have 3 variables here. That's A, B, and C. So conventionally, you'll have your left side of rows to be A and B, and your right side to be C. So, or to help, you can even sort of do A, B on this side and C over here, just so you're able to get the hang of it. All right, so this usually helps to do so. If it was 4, okay, you see how we do 4 variables in a video comment in the next question. So let's map this. X is equal to not ABC, so not ABC is going to be high, not AB, not C, not A, not B, C, A, B, not C, so A, B, not C, and A, not B, not C, A, not B, not C. Okay, so what we usually do, we'll fill this up with zeros. For now, that's what we're going to be doing, fill this up with zeros. So what do we do here? The idea is now to find what we call the prime implicant. Okay, we covered some rules for doing this in an introduction video. I will also link as a card in the top corner. But what you have to do is to find a group of ones that contain either 2, 4, 8 members, or it could be standalone. So you have a set of rules. You're looking for sort of rectangle, okay? Could be 2 by 2, could be 4 by 1, could be, how else could be, okay, 4 by 4, that will make it 8. Okay, so you're sort of looking at how can I, okay, so this will be 4, and this would be 4 2. This, if this were so, 1 2 3, 1 2 3, okay, this would be 4. So you're sort of looking at like a rectangular combination that will give you a number of terms inside this that are high that looks like this. So we'll see how we're able to do this, and we call these prime implicants. Okay, to really make more sense, the more we practice it. So the first one we can see is these two. Okay, there are a handful of rules for prime implicants, which is if a 1 can be in more than one prime implicant. That's one. Secondly, we were able to cover the wraparound adjacency in an earlier video. So this wraps around. So this wraps around with this way. This also wraps around with this way. So it's sort of a cylinder. You can think of Karnaugh Maps as a cylindrical. Let me see if I can draw it. So the wraps around itself. So it's not exactly a straight that's not a really good cylinder, but it's not exactly a straight line. Thinking of it as an enclosure really helps to be able to understand the wraparounds. But we'll get into, we'll solve as we're able to build the prime implicant. We'll see how we're able to arrive at these conclusions. So the first one we can see how I would do this is that I have 1 and 1 beside each other. So this particular box is going to be not A, not B, C, and this is not A, B, C. So I'm going to group these guys together this way as my first prime implicants. Okay, so these guys contain 2 and they are adjacent to each other. So this is a valid grouping. And I'm going to come here and I'm saying, okay, I can group these this way as one, and I can group this way as another group. So that we can, so now you can see we have 1 2 3 4 5 conditions where our outputs are setted, and we're able to make it into three prime implicants, three groups of ones. Okay, now an important thing to note is that as long as you're following the rules, you may not always have the same set of prime implicants as the person beside you, but as long as you do it correctly, you will still end up with the right answer. So for instance, I could also, let's get the rectangle up. I could also do this, then do this, then do this. So you can see that this is still a proper group of prime implicants, 1 2 and 3, and both of these will give me the same answer. All right, so as we solve, we'll get to see that. So let's solve this actually. So one thing I usually do to note is that we have a 3-variable Karnaugh map. Okay, so we have a 3-variable Karnaugh map. All right, and the maximum number of terms is 8, since this is a 4 by 2 box. So if everything were filled, the number of terms I'll be expressing to define it would be just 1, since it would be high. What do I mean by this? Imagine if instead of the zeros, everything inside this condition was full, was asserted, was raised high. So 1 1 1 1 1 1 1 1. That would mean that the output doesn't depend on the state of the inputs. So our condition X would always be true, which would be 1. Okay? If I have 4, I will expect 1 term to define it. Okay? Ooh, okay, so let me make this true and use 1 here. So this would be always true. Always true. If everything in my 3-variable Karnaugh map was high. But if I have a prime implicant of 4 minterms, so let's say I had 1 2 3 4, then only one variable would describe it. Okay, we covered this in the video where we introduced Karnaugh Maps and spoke about adjacency. Okay, what do I mean by this? If I had 1, 2, okay, let's draw a Karnaugh Map. Okay, 1. Ooh, this is not pretty even. Okay, but we have to make do with this. Sadly, okay. So let's say we had C and not C. C and not C, A not B not C. So if this were 1, 1, 1, 1, then my prime implicant group will have 4 terms, right? So the number of variables that will describe this would just be whatever is in this column C. Because since this changes across not A, not B, not A, B, A, B, and A, not B, it doesn't depend on the state of this. All right. If I had to, it would be 2 variables that will describe, okay, that will describe it. So let's get the boxes out. Okay. So if I had to, it would be 2 variables. And if I had only one, it would be 3 variables. Pardon my handwriting. It would be 3 variables. Okay. It would be 3 variables. As we solve, it will be easier to understand. Okay. So let's just do that first. And we'll come to understand what I mean as the more questions we solve in both these videos and the ones upcoming. So we picked these as our prime implicants across here. So let's label them. We can call this prime implicant 1. Okay. We can call this set 2, and we'll call this set 3. And we'll call this set 3. Okay. Call this set 3. All right. So let's try and come up with a Boolean expression for set 1, which is the point of Karnaugh Maps. So what I usually do is that okay, let me get this somewhere. Okay, recall this was set 2. Okay. Is that across this region, between these 2 columns, A is asserted, okay, because this is 1, 1, and this is 1, 0. So the value of A between these 2 rows stays the same. So that means anything in this column is going to have A high. So I can just sort of write here to be A to keep me kind of grounded, to remember if I have anything cutting across these 2, it's going to be A. So if I were to do this for B, it would be this way too. So highlighting this column, remember this is 0, 1, and this is 1, 1. So the value of B stays constant between 0, 1, and 1, 1. So I can write B here to remember that between these 2 rows, B is constant, B stays the same. And then the same thing applies for C. Oh, no, C is going to be only 1. Okay, since it's the only variable on that column. Okay, so C. So we'll see why this makes things easier for us as we get on solving Karnaugh Map questions. So for our set 1, we need to come up with a binary expression. So this cuts across. This is 0, 0. Okay, so looking at this, across this is in this cell and in this cell. So across this cell and this cell, B changes value from 0 to 1, meaning that our prime implicant number 1 doesn't depend on the value of B. But since A stays constant, it's 0 here and it's 0 here, we know that A is going to be involved. Okay, and since it's in the C column, we can say that the set 1 is described by AC. You understand what I'm trying to say? So the same way I said, if it were 8, it would be always true. If we had 4, it would be 1 term. And if we had 2, it would be 2 terms. So that's what I kind of meant here. Since we have 2 terms in this prime implicant, then that's 1 and 2. Then we'll need 2 binary variables to describe it. Okay, so which was AC, as we can see here. Let's practice with number 2. So with our set 2, let's look at it this way again. The value of C, the value of this set. So we have AB, not AB, not C. So for set 2. So set 2 is not A, B, not C, and not AB, C. So you can now kind of tell the value of this set cuts across both not C and C, meaning that the value of C doesn't change, the state of C doesn't change the truthfulness of this set 2. And it is entirely across this row here, meaning that this set 2 is described by not AB. You can think of it this way. If I were to write this out, how would I factorize this? Not A, B would come out, and I will have C or not C. Do you understand what I'm saying? So at the end of the day, you will now end up with AB. So if you can't really do this visually, you can write out the set of prime implicants and try to do a factorization. All right. So I have not AB, C or not C, which is going to leave me with not AB. So I'll write that for my set 2, not AB. For prime implicant 3, I see that. Okay, we can actually try and write this out. So set 3 is made up of, so this is AB not C, and this is A not B not C. Factorizing this out, what do we see is common? We have A and not C, and we can now also do that from the what we're able to highlight, because this prime implicant set cuts across the region where A is valid and is in the row for not C. So factorizing this out, we would have A not C, B or not B, which leaves us with A not C, and we can write this as A not C. So it's really as simple and elegant as that. So to now finish up the Karnaugh map problem, we are now going to or what we got for each term. All right, so we now have X is equal to AC or not AB or A not C. We can try and do a handful of manipulation with this. So we can bring out A, C or not C, or not AB, which will give me A or not AB. All right, so this is X. So now we're able to do the Karnaugh map expression. We can really verify this with the truth table. All right, but this is just so now we're able to point out prime implicants, make our prime implicants, get the variables for each of them, and or them together to get the final expression. All right, so let's solve one more problem. Simplify the following using a Karnaugh map. Y is equal to not A, B, not C, D, or A, not B, not C, D, or not A, not B, not C, D, or A, B, C, A, or A, B, not C, D, or A, B, not C, not D, or A, B, C, D. Pardon me. Okay. So, what's the first thing we're able to identify? Thankfully, I can say that this is a standard SOP. Okay. How are we able to tell? The domain of this expression, okay, which is the set of all Boolean variables involved, includes A, B, C, and D. And each term has each of that or their complements. So we have not A, B, not C, D here. A, B, not C, D here. So that means we're pretty good. And all we have to do is jump right into assigning. So we can do that. So we have not A, B, not C, D. Make this high. A, not B, not C, D. Make this high. Not A, not B, not CD, AB, not CD, and ABCD over here. Okay, so we can fill this up with zeros. Okay, so this is going to be a pretty simple setup. So you may look at this and say, all right, so let's try to make a primary implicant for this and do this 2 by 2 by 2, which is valid and it works. But keep it at the back of your mind that what we're trying to do is minimize the function, meaning we're trying to get the biggest primary implicant possible, which means the smallest number of prime implicants. Okay, remember the number of allowable terms that we can have, and then we can see that, hey, this box is everything here on this column is entirely adjacent, meaning I can group this as one prime implicant. Okay, and since this is directly next to this, I can join these two. So now I end up with 2 prime implicants, which is going to make my solving a whole lot easier. So now that we have 16 possible states, we can say that if we have 16, it's to be always true. Meaning that if everything in our Karnaugh Map was 1, then it's to be always true. That's what I mean by 16. But if it were 8, if there were 8 in our prime implicants, it will be defined. We'll define it with only one variable. If it were 4, we'll define it with 2. If it were 2, with 3. And if it were 3, with 4. You see, it's just so you know, you kind of have it at the back of your mind the number of variables to expect when defining. But we'll do it too this way. So we have to, this is 1, and we can call this 2. All right, so we have A here. Okay, and we've got B here. Cool. C and D, the same should apply, so let's do that quickly. C. D, okay, because this is 0, 1, 1, 1, and 1, 0. So since 1, 1, and 1, 0 both have C in common, C is asserted here. So you kind of get it. So let's go. For our primary implicant number 1, all right, we have A not B. So let's, in case you can do so visually, if I write to this visually, I would see that this runs across the entire column, not CD. And this means this would always be, this would simply just be not CD. Since it is true both for 0, 0 and for 1, 1, then that means it doesn't depend on the states of either of them. Okay, but we'll come to, you can get this algebraically if you write out all the terms. So I have not A, not B, not C, D, not A, B, not C, D, A, B, not C, D, A, not B, not C, D. Kind of rhymes. Factorizing this, we can see that not C, D is common to each of these, and which is why you have not C, D here. Because it's pretty, you can do it visually, or if you do have problems with that, write out each term in the cell, each cell identifier, and try to factorize it. So cell 1 is CD, and writing for primary implicant group 2. Okay, so this should have 3 terms. So let's look at it. The reason why we did this is that now we can see that this is entirely across this region where D is asserted. So all we have to do is pick the row, which is AB, and then D. So this is why I sort of did what I did. So this is now A, B, D. If you were to try to verify this manually, you write the value for each cell. So that would be AB, not CD, and AB, CD. What do we have common? A, B, and D. A, B, and D. Just to give you A, B, D, C, or not C, and we know how that goes. This return to 1, giving you A, B, D. Same thing we get. So this is why I sort of do what I do around the body of the Karnaugh map to make the visual picking of the regions of the prime implicants more visually clear. So a prime implicant is what each of these boxes are called. These group of minterms. That's our one. Okay. So solving this now is just to simply write out that y is equal to not C, D, or A, B, D. You really can't factorize out D, so you can have D, A, B, or not C. So you can now really see the usefulness of Karnaugh maps. See what we had at the beginning. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, and you can see how long this expression was. And what we were able to do with Karnaugh maps was to find out the simplest way we can write this, excluding all that we didn't need. So questions on this may involve, drawing truth tables with your new expression to verify this, drawing the combinational logic circuits. We'll definitely get to that in other videos. So this is just the first set of questions we're going to solve with Karnaugh maps, and we'll keep on going in other videos. So see you in the next video.